Okay, so in this video we're talking about modeling with exponential functions. In particular, we're going to talk about exponential growth, exponential decay, and also compound interest and continuously compound interest. So exponential functions are used to model a lot of real-world stuff. So that's what we're going to focus on in this example. So first off, in general, an exponential function is y equals a times b to the x power, where a cannot be 0 and b cannot be 0. So just keep that in mind. If you don't have these two conditions met, then it's not an exponential function, so forget about it. You got something else. Exponential functions can be used to model exponential growth, and here's the equation for it, and exponential decay. Essentially, these two equations are exactly the same. The only difference is, for growth, it's plus in the middle. For decay, it's minus in the middle. And here's a key telling you what each thing it is. A is your starting amount of stuff. R is your growth rate or decay. And it's important that your growth rate or decay rate is always as a decimal. Sometimes it's going to be given to you as a percentage. You'll need to turn that into a decimal. Very, very important. T is the time in years, and then Y is your final amount of stuff. And typically our stuff is going to be population, okay? So like the population of wolves in a forest, okay? Or the population of bacteria in a petri dish. So something like that. So let's do a couple examples. All right, so in January 1993, there was about 1,313,000 internet hosts. That essentially just means websites. During the next 5 years, those increased by about 100% per year. The very first thing we want to do is write a model giving the number h in millions of hosts t years after 1993, and then figure out how many hosts there were in 1996. Okay, so let's work on part A first. Part A, I'm going to do in green. So, first off, we need to determine what type of equation this is. We're talking about exponential growth, exponential decay. So far, those are the only two equations that we've had, so it's either growth or decay. Well, during the next 5 years, they increased. Increase means growth. So the model I'm using is h equals a 1 plus r to the t power. Again, on the previous page, we said y was your final amount of stuff here, just because they told us to use h, using h for your final amount of hosts. Alright, so A was our original amount of hosts, so let's write that out. And I'm just going to call that 1.313 million. Okay? Instead of writing out the whole number, I'm just using a little bit of scientific notation, 1.313 million hosts. And the reason why I'm doing that is because when I use my calculator and plug in stuff, I want my numbers as small as possible. Otherwise, I'm going to have to zoom a lot, and I don't want to do that. All right, my growth rate was 100%. So 100% as a decimal is 1. All right, and then finally, T is the amount of time in years. And I'm just going to leave that alone, okay, for now. So my original model is h equals 1.313 times 1 plus 1 to the t power. That's my original model. Write a model. We did that. Now, obviously, we can clean up our model just a little bit. 1 plus 1 is 2, so h equals 1.313 times 2 to the t power. Now that we have our model written, we can plug in for t or we can plug in for h and find out whatever we want to find. For instance, in part A, we want to find how many hosts there were in 1996. Well, what we have to pay attention to is T is the years after 1993. So we need to figure out, all right, well, in 1996, how many years after 1993 is that? Pretty easy. Scratch work on the side. 1996 minus 1993, that's 3 years. So this is our T for this particular problem. So when we plug in 3, h equals 1.313 times 2 to the 3 power. I'm going to use my calculator to help me out because this is going to be, just challenging to do on your own. So 1.313 parentheses 2 raised to the 3 power. Again, that 3's up in the air, so if you want to type it in correctly, you've got to hit that power key, or some people call it the caret key. Be sure you do that. Hit enter. And remember, our host, this is our units, are in millions. So this is 10.504. And notice how I made a complete sentence. there's going to be 10.504 million hosts in 1996 because I want to answer the question completely. How many hosts were there in 1996? About 10.504 million hosts in 1996. Okay, so we can graph this model. Now, keep in mind that your calculator only understands x and y. So, to do this, I'm going to do part B in green. To do this, I'm just going to say, all right, y equals 1.313 times 2 to the x. And I want to graph this model. I'm going to do that in my calculator. Okay. Again, this is all just y1. So 1.313. Make sure you type it in correctly. For whatever reason, I'm struggling with that today. And I want to graph it. So that's what it looks like. So as you can see that the number of hosts, this graph represents the number of hosts increasing over time. The number of hosts is increasing really, really fast. Okay, so now we got a graph. Let's look at what part C is asking us to do. Use the model to estimate the year when there were 30 million hosts. Okay, so we want to know the year. Again, our year is t, in this case x. So let's do the last part in blue. So what we want to know is 30 equals 1.313 times 2 to the x. We're trying to find x time. But this is pretty easy. Y, we already got this in y1, so let's call this side y2, y1, and let's start graphing. So y2, I got 30. Graph and zoom 6. Now, I might have to zoom out a little bit because I only see my original graph. I know I should have something representing 30. So I'm going to zoom out. And there's my point of intersection. So let's find that. Second calc, option 5. First curve enter. Second curve enter. Yes. So again, I'm solving for x. X represents time. So in this particular problem, this situation, it's going to take about 4.51 years to reach 30 million hosts. Okay, so that's it for this problem. Pretty much the big thing I want you to pay attention to is we did this in a progression. First we wrote a model, just a general model. Then we use that model to plug in for our time, to find our output. Then we graph the model. Once we can graph the model, we can plug in our output and find the specific input. In this case, we plugged in 30 and found that it took 4.51 years to get to 30. Okay, so doing this type of thing, plugging in what you know and solving for what you don't know, either by hand or by graphing, is a very powerful tool. Excuse me. Let's do another example. You're going to buy a car for $24,000. The value Y of the car decreases by 16% each year. We want to write an exponential decay model, so we're already told what type of model we want, and use that model to estimate the value after 2 years. So let's do part A first in red. So again, we're starting with our model. We're told it's exponential decay, so we're going to use the model y equals a 1 minus r to the t power. Let's plug in what we know. So our A is our starting amount of stuff. In this case, 24,000. So 24,000. So again, instead of doing the whole number, I'm going to just pay attention to my units. Very important. R was 16%, so as a decimal, that's 0.16. All right, and then T is just going to be left alone. So our general model is y equals 24, 1 minus 0.16 to the t power. I want to clean this up as much as I can. So y equals 24, 1 minus 0.16 is 0.84. I don't know why that went to green all of a sudden. Let's go back to red. And still to the t power. Now we're going to use that model to estimate the value after 2 years. So here t is 2. Using that, we now have y equals 24 times 0.84 to the 2 power. I'm going to use my calculator to help me out. We have the technology, so why not use it? So 24 parentheses 0.84 raised to the 2 power. So my car, so essentially this number here is telling me that my car my car is going to be worth approximately $16,930,000. Or it's very close. I'm just going to go ahead and round up and say Y is about $17,000. Okay, so my car is approximately about worth $17,000 in 2 years. I just rounded up a little bit, not a big deal. More accurate was $16,934,000. Okay, so that kind of makes sense, but car depreciation is pretty rough. I mean, you originally bought it for $24,000 and you've already lost $7,000 in 2 years just by driving it around. That's not even including if you got in a wreck or a ticket or anything like that. So who knows how worthless your car would have been in 2 years if you got in a wreck. So just keep that in mind. All right, we want to graph this model. So again, we're going to go back here. So we're going to do part 2 in green. So I'm going to say Y equals 24.84 to the x power. So here x is just going to replace time temporarily. So we can graph it. So let's go ahead and graph this. I'm going to graph it at Y1, clear out everything else that's already there. All right, and then zoom 6. And so what we can see is that the value of the car is decreasing over time, which kind of makes sense based on what we know is supposed to happen. And then we want to use the graph to estimate when the car is going to have a value of $12,000. So what is our final amount of money? So again, it's $12,000. So I'm just going to put in a 12 equals 24. So 0.84 to the x power. And just like we did before, we already have this side of Y1. So I'm going to put this side of Y2. So now let's graph. All right, and I'm going to zoom out a little bit. There's my point of intersection, so second calc, option 5. First curve enter, second curve enter, yes. So about 3.97. Which is about 4 years. The car is worth $12,000. Okay, so in a little bit before 4 years is done, your car is only worth $12,000, which is half of what you paid for it. So you're losing money pretty fast on this car. But that's typically how most cars go. Most cars don't hold their value very long. Okay, let's move on. So we just talked about exponential growth and decay. Exponential function can also model interest. Okay, so interest, this is pretty much what happens when you go to the bank. So we're going to talk about what kind of happens on a normal basis and then what the ideal situation is. So on a normal basis, you have what's called compound interest. And you have this equation. You need to make sure you know it. Here, P is called the principal. That's the original amount of money in your account. R is your interest rate. Again, we want that as a decimal. N is the number of compounds per year. So how many times does the bank calculate the interest that you owe them? Okay, so that's N. And then T is the time in years. On the other hand, if you're getting your interest in compounding continuously, that means it's happening every instant of time, which I'm going to tell you, no bank does this. This is just kind of the ideal, perfect situation. But no bank is going to do this. So just hypothetically, P is still your original amount of money. E is approximately 2.718. That's an important number you should know, kind of like pi. We're going to, however, hit the second decimal key to get E. We'll see that in just a minute. And then R is your interest rate as a decimal. That's very important. And T is the time in years. So make sure you know both of these equations. Let's go ahead and use them. All right, so you deposit $1,000 in an account that pays 8% annual interest. Find the balance 1 year later if the interest is compounded with a given frequency. So part A, let's do it in red. All right, so compounded annually. So that means compounds are the number of times per year that the bank calculates your interest. So annually means that N equals 1. Okay, and since it's not compounded continuously, we're going to use the formula A equals P times 1 plus R over N to the NT power. Well, we already know what N is. P is 1,000. P is 1,000. 8%, that's our R, but we want that as a decimal, so 0.08. Okay, and then T is 1 year. Okay, so that's what I suggest you always do, is go through and label your problems. So I'm going to plug in what I know now for part A in red, and I want to calculate how much money I'm going to have in the bank after this 1 year interval if the interest is only compounded annually. So I have A equals 1,000, 1 plus 0.08 over 1 to the 1 times 1 power. Just plugging in everything that I know. Now, I have a fraction here, so when I type this in my calculator, I want to be sure to put that in parentheses as well. Every time you have a fraction, it needs to go in parentheses. Also, don't forget, since this is a power, you need to hit that power key. So what I suggest is you actually draw it out. That way you're pretty guaranteed to type it in correctly. So I'm going to go to my main screen and just type this in, 1,000, parentheses 1 plus 0.08 divided by 1, close parentheses, parentheses again, power. And I've got more than one thing up there in my power, so I'm going to put parentheses on that, 1 times 1, enter. I end up with $1,080. So in the end, in this situation, I get $1,080. That's my A. Okay, we're going to go through and do the same process. Quarterly means that I'm getting money from the bank. They're calculating interest 4 times per year. So my equation that I'm going to use is A equals, I'm plugging in what I know, 1,000, 1 plus 0.08 divided by 4. That's a fraction, so put extra parentheses around it. Raised to the 4 times 1. I have more than one thing on top, so I need parentheses around that. Ready to type that in now. So I have 1,000, parentheses 1 plus parentheses 0.08 divided by 4, parentheses raised to the parentheses 4 times 1. I get 1,082.43. So since my number of compounds have increased, I've actually got a little bit more money. Let's see what happens next. Here, if I'm compounding daily, well, we're going to say, since it's a bank, we know banks are only open a certain number of days of the year, like they're closed on special holidays like Christmas and stuff. So we're going to use banking days, which is essentially N equals 360. Okay, so that's the number of compounds per year. We're going to plug in what we know now. So A equals our starting amount of money times 1 plus our interest rate divided by the number of compounds, 360. That's a fraction, so it gets the parentheses around it. Raised to 360 times 1. Okay? Again, write it out as best as you can. That way you're pretty guaranteed to type it in correctly if you know what you need to type in. 1,000, parentheses 1 plus 0.08 divided by 360. Make sure you type it in right, because if you mess up, it's going to change the problem. Raised to parentheses 360 times 1. I get 1,083.28. Here I'm just rounding to the nearest penny. Hopefully you picked up on that. But again, my number of compounds per year has increased, and each time my final amount of money is getting a little bit bigger. Okay, so now let's go for the ideal situation. If I'm compounding my interest continuously, that means every instant in time, my bank is giving me a little bit of interest. Again, this is the ideal situation, but in real life, this never happens. The bank is greedy. They're not going to give you that much money. So here, since it's continuous, we're going to use the formula A equals P E to the RT. E is just a number that we're going to use in our calculator. P is still our original amount of money. R is still our interest rate, 0.08. And T is still our time. We're talking about 1 year. Okay, so let's plug in what we know. 1,000. E raised to, we have more than one thing up here, 0.08 times 1. We're going to plug in what we know. So in our calculator, 1,000. Now to get to the E, again, you hit the yellow second button, and then the divide key, raised to, we have more than one thing, 0.08 times 1. Make sure you type it in correctly. If you make a mistake, fix it real quick. And then you get 1,083.29. And that's your final amount of money. So, again, continuously is a little bit better than getting compounded daily, but not that much better. Obviously, you want to try to find a bank that's giving you as many compounds as possible because essentially interest is free money. So you want as many compounds as possible. Unless, of course, you're paying interest on a loan or a credit card, then you want as few compounds as possible. So those are important things you need to keep in mind. Okay? And that's it for this video. Let me know if you got questions.